Welcome to the next video on discrete math. This is video 5 on the Josephus problem, and it corresponds to chapter 1, section 3 of the textbook. So to give a colorful little story behind our math problem for today, Josephus was a historian of the first century, and by a legend, possibly apocryphal, during the Jewish-Roman War, he was among 41 rebel Jewish soldiers trapped in a cave by the Roman soldiers and about to be, killed by them or enslaved or something like that. Preferring suicide to chapter, the rebels formed a circle and made the following agreement. Rather than commit suicide themselves, they would kill each other effectively. And so the way that they would do this is proceeding around the circle. They would kill every third person until none were left, right? So if you imagine that you've got your circle here and people are all around it, then we could start with this person and they kill the person next to them. Then we go to the next person who kills the person next to them, and then the next person kills the person next, and then they kill that person next. Now, returning back to the start, this person kills that one, and then this person kills that one, and then this person kills that one, and then only the last person alive has to commit suicide. Now, Josephus himself did not want suicide, right? Did not think this was a good idea, didn't want to join in on this. I don't know if he planned to hide or run or just give up to the Romans. I don't know the history there, but he didn't want to commit suicide. And so with a co-conspirator, he planned to place himself and his conspirator in the circle such that they would be the two last people after everyone else had been killed, and then they would simply not kill each other or themselves and just do whatever they were going to do. Now, for simplicity and also for generalization, right, there were 41 of the Jewish soldiers. We're going to generalize to any n people, but we're also going to simplify a bit and talk only about and I described it as killing every other person, every second person. They did every third person, but the idea is very similar. So we're gonna work with the assumption that we're talking about every second person. So let's do a concrete example and try to work out. Right, we're going to call j of n. That's going to be our function, which says, if you have n people, then j of n is the location around the circle where you want to be last. So if we draw this diagram, which goes up to 5, right? So 1, 2, 3, 4, 5 around the circle. And let's simulate this just to see who happens to be the last in this choice of n. So the first person kills the second, the third person kills the fourth, the fifth person kills the first, and then the third person kills the fifth, right? So that leaves person number 3 at the very end, which demonstrates that j of 5 equals 3. Just to get, this is all just for the sake of warm-up, right? We want to solve this for a general n. We're basically trying to figure out what is this function j of n. That's really our problem. But this was all just to do a walkthrough just so that we understand the problem. Now, if we collect some data, we can get a little bit more traction on what's going on here. And so when n is equal to 1, j is equal to 1. That's very easy to see because just the one person around is, the only choice, right? They're already the last person in the system or whatever. If you have 2 people, then the first person kills the second, and then the first person is the last one alive. So when n is equal to 2, j is equal to 1. Okay. When n is equal to 3, so the first kills the second, the third kills the first, so the third person is the last one alive, and so on, right? And so you can complete the rest of this table. The textbook has more of the data filled in, but one thing is obvious in the table and also just logically, which is that the correct answer is never going to be even, because the first time you make a pass around the circle, every even number, right? 1 kills 2, 3 kills 4, so on, in all of the even numbers are going to get eliminated. So the answer is never even. But also, like, having sort of done that simulation, think about what happens when you kill the last even person. Then effectively you've got the circle all over again. And you're going to make another tour around just with, approximately half the number of people around the circle, so that it is like the same problem, but for a smaller n. And like, if you think about how any one of these odd numbered indices around the circle corresponds to the index, right? When you like re-index everything, right? Reset everything back to 1. And here what I've done is I've drawn the situation when we have an even number of people, right? When n is even. And in that case, effectively, this 3 is going to correspond to times 2 minus 1, right? That gets you to 5. Right? This 4 corresponds to 7, and again, they're related by the formula times 2 minus 1. What this kind of does is relates the smaller quantity, let's call it m here, right? So for half as many people, the way that it relates to the sort of system when there are twice as many people is this formula that we just said, times 2 minus 1, right? That's how all the indices are related to each other. And in particular, right, whatever index is the last survivor in the bigger system, then is going to have, their formula, their index related through this formula, right? So like basically, whatever is the solution to the big system is the same as the solution to the smaller system related through this re-indexing formula. So we get this recurrence relation, right? That's kind of the point here, right? Is that this is how we relate the answer to the bigger system to the answer to a smaller system. This time smaller, not by 1, but by half. Now I'm going to skip over all the details because the argument is very similar, but when you have an odd number of people, then the relationship is given by this formula. So for going from some particular quantity to times 2 plus 1, right? Like that's getting you to an odd quantity of people around the circle. Then the indices, right? The relationship between the indices is given by times 2 plus 1 this time. Now, this may seem a little awkward, and it is a little awkward to have one formula for the evens and another formula for the odds, but notice that it is perfectly adequate. We already said that j of 1 is equal to 1. And so from that starting point, we can use the even formula to get j of 2, right? So j of 2 must be equal to 2j of 1 minus 1. And then since j of 1 is 1, then we simply perform that substitution, compute, and we get 1. And notice that that 1 is in complete agreement with the 1 in the table. So that seems to have worked out very well. What about 3? Well, we use the odd formula, saying that this is the same as 2 times j of 1 plus 1, right? That's the formula relating something to 2m plus 1. And according to this formula, then we would, to get j of 3, we would compute 2 times 1 plus 1, which gets us 3. And again, looking back up at the form or the table, we get 3, so that makes perfectly good sense. So these recurrence relations seem to be confirmed. But at this point, right now that we know the recurrence, we'd like to solve the recurrence And the method of solving the recurrence that I displayed in the previous 2 times that we had to do this thing that I called unrolling, we can't do that here, right? Because basically the fact that there's like one formula for the evens and a different formula for the odds means that as you go through the process of unrolling, right, performing each next expansion, you don't know whether you need to do the formula for the evens or the formula for the odds. So that strategy is not going to work. So maybe what we do is, and I don't know how realistic this really is for how actual mathematics gets done, that you actually like compute a bunch of cases and then hope to see a pattern, but at least it works in this case. And so if we, draw out a fuller table and we look harder at this pattern, we see that, well, okay, there's a lot of ones and they seem to recur, right? So we've got a 1 here, but then we get a 1 and then a 3 here. And then we get 1, 3, 5, 7, okay, and then from here it kind of goes off the table, 1, 3, 5, 7, 9, and you'd maybe want to, I think actually the book has more terms than this, and you'd notice the pattern even more convincingly, but I think this is enough to see that that here, we start at 1 and we have a length of 1. Here we start at 1, we have a length of, 2. And we skip, right, we go to the odd numbers. Then here we have a length of 4, which I'm going to call 2 to the 2. And we, again, skip so that we take only the odd numbers. And so presumably, if the hypothesis works out, this would have length 2 to the 3, which would be 8. Instances, again, skipping so that you hit only the odd numbers. So if this pattern is correct, and for now it is just a hypothesis, but it will turn out to be a correct one, then what this would mean, right? If this pattern persists, then to get j of n, we could find it by doing the following. Find the least power of 2 which stays under n. So let's go sort of simulate this somewhere. Let's pick a number, and I want to pick maybe a nice random seeming one. So let's talk about this 10, right? So we're going to find the least power of 2 smaller than 10. So that would be the 8, right? 8 is the least power of 2 smaller than 10. And that's right, and just noted, like that's where these blocks begin, right? Each block begins at some power of 2. So to find the beginning point of a block, then we take this power of 2. In this particular case, that would be 2 to the 3. Now, from here, we sort of count out how many steps we have to go until we reach our given number. In this case, that's 2. So we would want to represent 10 in this instance as 2 to the 3 plus 2. And so what we're going to do is we're going to call this m. M is going to be the least power of 2, which is smaller than or equal to our given number. In this example, our given number is 10. And then we're going to call this L. So L is just going to be how much more you have to go after that to reach our target number. And so if you take any given number, right, say take any n, you can always decompose it into the least power of 2 that stays under plus an L, and that L can always be chosen from 0 to 2 to the m, inclusive on 0. That's in case you have exactly a power of 2, or up to 2 to the m exclusive. If it were equal to 2 to the m, then you would in fact be at the next power of 2, so we don't want to go that right. Then you could have chosen a bigger m for this 2 to the m, so we don't want to go that far. And what it seems is that once you find those steps, right, L is the number of steps, and remember, every time you take a step, you get an odd number. So we want to take the odd number that many steps out, which is to say 2 to the L plus 1. And here is our hypothesized solution to the problem. If you appreciated this content, please like and subscribe. And if there's anything that we discussed here where you'd like to see it elaborated further, I might be able to answer questions in the comments, or for substantial topics, I might make an entire video and add it to the playlist.